get this first session started on planning and programming tools. The question that we really want to answer here is, how do you visualize the planning and program process from data collection to performance monitoring? And we've got three exciting speakers. Our first presentation is from Federal Highway on highway externalities, the inequity identification tool. Viktoriia Dunleavy joined FHWA as a data scientist statistician nearly 3 years after working at the International Monetary Fund. Possessing a master's degree in business analytics from George Washington University, she is a leader of data management, inventory storage, and dissemination initiatives. Viktoriia is passionate about data analysis, big data, AI, and enjoys promoting different methods for improving policymaking processes through data visualization. And Thor Dodson is an economist with the Federal Highway Administration, the Office of Policy. He works on the Externality Cost Assessment Tool, or ECAT, the National Highway Construction Cost Index, the NHCCI, conducts benefit cost analysis review of highway projects for discretionary grant programs, and provides support for a variety of projects in the Office of Transportation Policy Studies. Let's welcome our speakers.
Thank you, everyone. So I'm Thor, I'm an economist. This is my colleague, Viktoriia, statistician. So we work in the Office of Policy, and today we're going to talk about externalities of highways, specifically some tools we've developed recently to visualize the cost estimates, as well as the spatial distribution and trying to quantify the actual equity of those exposure to negative highway externalities. So who are we? We work in the Office of Transportation Policy Studies. That's part of the Office of Policy and Governmental Affairs. We have a wide variety of backgrounds, including economics, operations research, engineering, transportation planning, statistics, political science, public administration. You know, we're in a very cross-sectional space, so we really lean into a lot of these backgrounds. It really helps us do what we do, which is a lot of research. We conduct research into transportation policy, legislation initiatives, as well as implementing and facilitating these through strategic planning. We develop a wide variety of tools and methods to support the decision-making. Some of these tools include, we've worked on the highway cost allocation study, examining the relationship between investment, transportation performance, economic productivity, as well as truck size and weight policy, mile-based user fee, emerging transportation policy issues, a wide variety of interesting projects related to transportation. So we do this a lot for agency leadership, the transportation secretary, as well as other administration officials, and we also respond to congressional committees that make requests for our office. So what is our purpose today? We want to provide you an overview of the Externality Cost Assessment Tool, ECAT. We'll showcase the ECAT results dashboard, a place where we're hoping the results can be easily accessible for use by practitioners and planners. Then next, we'll show an overview of the work we've done applying ECAT for equity analysis, specifically the inequity identification tool, which is a mapping platform to visualize the results we found. So what is ECAT? Externality is sort of an economic jargon term. It means in this case, we're talking about quantifying the negative impacts from the use of the highway system that are caused by, but not fully paid for by, different classes of highway users. So here we're thinking about what are the side effects of highways? Costs generated from highway use that the users are not themselves bearing. So we talk about noise, air pollution, crashes, and congestion. Costs that affect people that aren't actually doing the driving or use of the highway system. So to get these estimates, ECAT brings together various model results, elasticities, and data. And it was originally designed to support the highway cost allocation study, looking at the cost allocated to different vehicle classes. But it can also support tax policy, benefit cost analysis, discretionary grant reviews, and transportation regulatory analysis. So what can ECAT do? Fundamentally, it can produce outputs to support policy decisions and project cost analysis. And it can do this in terms of external total cost per category, average cost per VMT, and in some categories, the marginal cost per VMT. It can break these costs down by state, by vehicle type, by highway functional class, as well as by rural and urban areas. And due to the inherent uncertainty in some of the models and parameters that are used to generate these estimates, we have a range of low, medium, and high scenarios. So a brief overview of what we have so far is noise pollution, which we estimate the total cost is around 11 billion, although we had a symposium in the last couple of days where we heard that cost may be a lot higher if we use a different methodology, which we're looking into. But currently the way we do this is we translate traffic volumes and speed into noise. So we look at the noise coming from highways, and then we use what's called the hedonic approach, or the indirect valuation, where we're assuming that people are internalizing the cost of this noise through their valuation of the housing market. So there's a large literature on this looking at what is the change in housing prices with exposure to different noise levels, and we use that as our basis to estimate the cost. Although we're exploring looking at the direct cost, because there are a lot of studies looking at the health impacts of exposure to noise over time. The next category is air pollution. This is a much higher magnitude so far. We estimate it's around 215 billion. And we do this through a combination of EPA models, MOVES, which allows us to get the emission rates from vehicles, as well as a model called COBRA, which can simulate the health costs from a change in ambient air quality. So we use our traffic data combined with emission rates to look at what is the impact on air quality, and then what are the health costs of that air quality. And the costs are very sizable. Additionally, we also calculate the cost of greenhouse gas emissions using MOVES, which estimates the emission rates for greenhouse gases, as well as the interagency social working group social cost of carbon estimate. The next category is traffic crashes. This one's a little more straightforward, although by no means simple. We look at the total number of crashes, both fatal and non-fatal, and we have a variety of techniques to monetize those crashes through the value of statistical life, as well as quality of life adjusted years. Congestion, we go segment by segment, looking at volume to flow capacity equations to estimate what is the delay on different traffic segment or road segments based on the traffic going through there. And then we have a value of time to monetize that. And we're also currently working on a method for estimating barrier effects. That is the cost generated by highways physically separating areas where it's difficult to cross or move around them, as well as the barrier effect presented from heavy traffic, because that can deter trips. It can be extra time or extra travel due to the physical difficulty of crossing busy roads. And this is well known as an impact that divides communities. So Viktoriia is going to take over next to show you the ECAT results dashboard. And our goal here is to make these estimates of the externality costs easily accessible. This can enable comparison of costs across states, across urban and rural areas, and across road types, as well as across different vehicle classes. And the cost is in per VMT format, which facilitates easy use and benefit cost analysis. If you can estimate the impact on VMT, something like induced demand or change in traffic loads. Okay.
Thank you.
Okay, here you can see the ECAT dashboard. And on the right top corner, you can see the tabs that we have here that will be your first tab to read about the ECAT dashboard, the methodology, and as well as the option to download the data from the Data Hub website. So here you can download the data and work on your own. But let's go back to the dashboard, to the home page, and let's explore the first, that we have two views. We'll have a graph view and a table view. And then here you see we have the ribbon of filters, and we'll start with the first filter, which is the state filter. We'll pick a couple states as well as the national. The next is the cost category filter. We currently have 5 externalities, 5 costs that you can choose from, which is delay, emission cost, noise cost, air pollution, and crash cost. For first examples, let's pick noise cost. Then we have functional system class. Interstate, freeways, expressways, other principal arterias, minor arterias, major collector, minor collector, and local roads. And the classification is based on speed, uninterrupted use, land access, and mobility. And next filter is the vehicle type. We have motorcycles, passenger cars, buses, light trucks, single unit trucks, and combination trucks. In general, the bigger the car, the more cost it can cause. So if we choose the passenger cars, single unit track, combination track. We're gonna see our graph already populated on the bottom. So, but let's move to the next filter, is the unit filter. We have a cost per mile, as well as the total cost in million miles. Next filter is the area. We have a weighted average, which is overall option, urban areas and rural areas. And the last filter is the cost range, which ranges from low, mid to high. We usually use the mid range, and for different projects, we can use low, which is 80% of the mid, or the high range, which is around 120% of the mid rate. As you can see that the graph, the middle graph will show you the cost, and the bottom graph is going to show you the annual VMT. And if you want to look at annual VMT based on the functional class, you can just click on the functional class up top, it will change in the bottom. Let's go back and look at the graph itself. So right now you can see how functional class can contribute to noise. For example, minor and major collectors contribute more to the noise than the interstate. If we switch to the urban area, we will see a difference. We'll see a difference in the noise cost as well. It's going to be much higher. So we're going to move some of the vehicle types, and we only look at the passenger cars. We can easily see how a functional system contributes to the noise cost based on the different states and based on the functional system class. So some of the other principal areas contribute more to the cost, as well as some states can contribute more to the cost than the other states. And let's explore our second example. We'll go pick some other states. We get our states in, then we'll select the next cost we're going to look at is the pollutant cost. We will add the local road and the functional system class. And the rest filters will stay the same. So right now you can see that how the functional system class contributes to the air pollution cost. So it's pretty much functional system class contributes at the same level, even for different states. So let's add some more vehicle types, like single unit tracks. We can see the same pattern, as well as the combination tracks. So now this graph is a little bit crowded. It's a little bit hard to read the numbers. That's why we built in a table view, which is color-coded, can help your eyes easily to identify the functional class or the state or the vehicle type that contribute most to the pollutant cost. Okay, and with that, I'll go back to the presentation and Thor will talk some more about the noise.
Thank you, Victoria. So as you can see, our goal there is to, So our goal there is to make the variety of external costs accessible. Because you see with a large number of filters, the costs vary dramatically across states, across vehicle types, and having all of that in a huge table is a little difficult to process. So we wanted to make that in a form that's easier to look at for practitioners. Maybe you're only interested in one state, but you want to compare across road types, or you want to compare across vehicle classes. All of that functionality is built into the tool, and so we're still seeking how to fine-tune that, because there's a lot of dimensions to showcase. So next I'd like to talk about the work we've done over the last year applying ECAT to equity analysis and the distributive impacts. So ECAT estimates the cost of externalities from highway use, but we wanted to extend this to estimate who is affected. And we've expanded the tool to analyze equity for noise and air pollution, because those are more easily localizable. We know where they're coming from, we know how far they go, so we have a much better idea of who is actually affected by that. The general approach is we estimate where does the exposure occur, and then we attribute the exposure, the cost of that exposure, to demographics of intersecting ACS census block groups, which has a population at a very fine spatial detail. Why do we want to do this? So we've already seen the cost of these externalities can be very substantial. Highway noise and air pollution, they're produced by users, but they affect people who are not actually using the system. This can result in adverse health effects, reduced cognitive performance, and diminished quality of life. And it stands to reason that households near highways absorb more noise and air pollutants. And if subpopulations or demographics tend to live near highways due to historical policy, gentrification, structural inequality, social capital, or other reasons, then highway externalities are contributing to inequity. And we believe the results, methodology, and the mapping tool can support efforts to target inequities for mitigation from the negative externalities of highways. So how do we do this for noise? So first, using our traffic to noise equations, we estimate the distance each sound level reaches from each highway segment. So if anyone's familiar with the HPMS data set, it has down to 1/10 of a mile often length of segments. And then we have the traffic data for those roads. So we estimate the noise coming from that road. Then we use the ACS data to look at the housing density near the road segment to estimate basically how many people are affected by that level of noise. Then, using the hedonic pricing literature on what is the cost of the noise reflected in the housing price, we can estimate the total cost from noise for each highway segment. Then we allocate it to different demographics based on the relative percentage within the intersecting census block group. So if a highway is intersecting a census block group with 20% non-white population, for instance, we would allocate 20% of the cost to the non-white population. So here we're implicitly assuming that within the census block group, all the populations are evenly distributed throughout the space, which of course is not always true. There's usually clustering in neighborhoods which can be actually closer to the highway or farther away. But until we have better detailed population data, this is the best assumption we can make. So finally, now that we have the cost allocated to each demographic for each highway segment, we can aggregate over a larger area. So say over a county, over a state, or even over the whole nation, and calculate what we call the noise equity ratio, which is the percentage of costs absorbed by a demographic divided by the percentage of the population of that demographic within that area we've aggregated over. Crucially, if this number is greater than 1, then that demographic's absorbing more than we could call the fair share. They're absorbing more noise cost than their share of the population. Less than 1, the reverse. So for instance, if you can imagine the entire population was randomly distributed through the whole country, there was no patterns, then this ratio would be 1 for all demographics. But as we see, that's not the case. So first, pay attention to the left 2 most columns. We can see that the white population absorbs significantly less than what we could call the fair share of noise cost, around 0.86. So it's 14% less than the fair share. While the non-white population, which is an aggregate measure of all the other demographics, absorbs about 38% more noise than the fair share. We can see how that's distributed across different demographics. And then the last 2 bars show us that we look at non-poverty and poverty, we see a similar effect. Non-poverty is absorbing less noise. It's around 0.97, I believe, while poverty is absorbing about 1.13, 13% more than what we call the fair share of noise. So this is aggregating over the whole nation. We can also aggregate over the states and see how does this inequity vary across states. You can see, on average, here we're only comparing non-white in the top set and then white in the bottom, and generally non-white tends to absorb more than the fair share of noise. We can also look at county levels. So here, each column represents a different county in Texas. The orange square is the non-white value, the blue square is the white, and I want to point out, on average, non-white is much higher than 1. It's like 1.22. But of course, this varies across space. Last point about this is it's really an urban thing. Over 90% of the noise damage we're observing is in urban areas, which is a little bit of a rough measure. You know, there's always suburban, exurban, various things. But this is largely because of this noise damage depends on the density of houses near roads, the amount of vehicle traffic, the speed of the traffic, and the traffic composition. That is how many trucks versus cars, because trucks generate a lot more noise. So in order to make these results palatable and understandable for practitioners who actually want to do something about it, we've made this mapping application to visualize the distribution of highway externalities. It combines the cost of the noise with the equity calculations to easily see where are the high cost noise roads, and then where are the inequities. We developed some case studies highlighting the historical legacy of highway placement. This tool can enable pinpointing of roads with high externalities for mitigation, and can also screen potential highway projects to understand the impact on equity. Is there an existing inequity there? Is this going to make it worse or better? And I know that noise is one of the sort of smaller externality costs in magnitude, but noise is actually reflective of all the other externalities. Even though the magnitude may be different from the other categories, the distribution tends to follow where the traffic is, which is where the noise is. So we believe this noise equity analysis is actually very reflective of other highway externalities and how they're distributed across demographics, across space. So briefly, I'll just talk through a couple case studies before we show the tool. Here on the left-hand side, we're looking at the equity ratio values for the non-white population at the county level. So darker red means higher, greater than 1. Blue means less than 1. And we can zoom in on an area we've identified that has a high noise inequity towards the non-white population. In this case, around Birmingham and Tuscaloosa. And then the second graphic, we've switched the layer to the percentage of population of non-white population at the census block group level. And then the roads, the thickness of the lines is showing the magnitude of the noise costs. And you can see a visual correlation between where there are a high percentage of non-white population and where the highest noise cost roads are. Similarly, we can look at, I was looking at a history of communities that were severed by highways, and identified Akron, Ohio as one of them. And then sure enough, looking at the tool, we can see there's a high noise inequity there. And then you can pinpoint, which roads are causing it, which neighborhoods are really being affected by the high noise cost. We've also built in a set of filters. So for instance, you can filter which counties are shown that have a noise equity ratio higher than a certain value, as well as filtering for the magnitude of the noise damage for each road segment to understand, which roads should we target, which areas have high inequity. So in the bottom right, we can see we filtered for roads that have greater than $500,000 per 1/10 of a mile, which are clearly good candidates for some sort of noise mitigating procedure. I have a couple more case studies, but for the sake of time, we'll jump right into the tool.
Okay, here's the tool, and first we're gonna be looking at the noise equity ratio layer, which is color-coded from the blue to red, and the 10 is represented the middle like 1. So we can easily identify the counties with noise equity ratio more than 1, which is gonna be the red ones, and you'll have a nice table here that will tell you exact number for the county for the non-white equity noise ratio, as well as the darker blue counties will represent a non-white equity lower than 1. And as a default, we're going to be looking at non-white option. So if we go back to the, let's turn this off, we'll go back to the actual layer. We have a symbology where you can actually pick a demographic, non-white by default, but you can choose any of what we have here. As well as Thor mentioned, we have a filter. So you can filter a non-white equity ratio if you want to see everything that's over 1.6, so really high. Or if you want to look at the non-white damage in annual dollars, in dollars, so if it's more than $2.5 million, you'll see the counties for that. And you can use both filters with and statement. So looking at the counties with 1.2 and the non-white damage higher than $2.5 million. So next layer is the noise damage layer. It's also color-coded by the bins. So the lowest bin would represent the annual noise damage less than 100, and the darkest, thickest line, bin number 7, will represent the noise damage over 1 million. So we also have an option to filter the noise damage by functional class. We want to look at the interstate, minor, major collector, or if we want to look at the bins. For example, we're only interested in noise damage over 1 million. And then if we will zoom in a little more to see the roads, we can actually see what roads contribute to the noise damage over the million. And if we want to look at what functional classes, we can play with this filter, and you will see when the highway disappears and appears back, or local roads not here. There are some minor arterials. So we can also quickly look at the urban areas. With all of that, we can see that the noise mostly concentrated in the urban areas. And let's quickly I show you how Thor finds the Syracuse by using both the noise damage and the noise acuity ratio layers together. So turn them on. Actually, turn this off. I'll back to Syracuse here. Zoom in on it. I'll turn this layer off. Turn the road layer on. We'll go back to the filter. We're only interested in the ones that more than 500,000. And we can clearly see the roads. We also have an option here to switch a map to like an imagery map. If we turn this layer off, zoom in really in on the communities there, we'll be able to see what community is affected by the road. And with that, if we want to explore more about the population on the communities, we're going to turn the population layer on. It's also color-coded. It's also, you can choose the symbology. It's set for non-white as a default, but you can choose any other population. And then we can see amount of non-white population that varies from the light purple, which is 0.2%, to dark purple, which is around 1%. So turn the road back on, just to see how it looks from far. And I think this is it for the presentation demonstration. I'll give it back to Thor. Oh, yeah, I also want to mention that we have the homepage. If you want to do any further research on that, we provided the future service options to download the data and play with the data. And we have kind of a story that tells you more about ECAT and the inequality identification tool. Okay, now back to Thor.
All right, so thank you very much for your attention. We're very excited to showcase this tool. We're not quite ready to publish yet, should be sometime next year. But we're very open to questions, especially feedback on applications. You know, how can we make ECAT work for you? Does this seem like something that's relevant? Any suggestions, of course. This is very important to us as part of understanding the full range, not only the benefits, but the cost of highways. So I think there's a lot of concerns about, you know, who is benefiting while who is bearing the cost of the highways. And we believe this is an important tool to try to shed light on actually quantifying that discrepancy. Thank you.
Excellent. So we've got